in some problems, we're interested in functions not for their exact values, but for the behavior of the function as x grows larger. Um, so for example, you might have a computer algorithm um, that requires some steps to compute, and we're interested in knowing how fast the algorithm is when you're performing millions of operations per second. Uh, so to measure how fast the algorithm is, we use the concept of growth rates of functions. So generally, we say that a function f of x grows faster than g of x if for large values of x we have that the function f is greater than g. Formally, the way we define it is that for functions f of x and g of x, which each of them go to infinity, we say that f of x grows faster than g of x if one of these two cases occur, right? So if you write the fraction g of x over f of x and compute the limit as x goes to infinity, if this goes to 0, then that means that the bottom function is faster than the top function. So that means that f is bigger than g. If you write the fraction in reverse order, compute compute the limit, and you see that the limit goes to infinity, that means that the top function is faster than the bottom function. So that means that f of x is faster than g of x. And then they have comparable growth rates if the limit is some finite number. Okay, so let's take a look at an example. So suppose I want to compare the growth rates of the following functions. So the first function is x squared times ln of x, and the second function is ln squared of x, so the natural log of x squared. Okay, so if I want to determine which one is faster than the other, I need to form this fraction using the two functions and then compute the limit. Okay, so let's put x squared ln of x on top, and then ln squared of x on the bottom. Okay, so now I have to compute this limit, but you can see that there's an ln on top and there's ln squared on the bottom, so we can cancel one of them out before computing anything. So canceling one of the natural logs, you get x squared over ln of x. Then now you see that as x goes to infinity, the top goes to infinity, the bottom also goes to infinity. So this is of the form infinity over infinity. So we can apply L'Hopital's rule. So taking the derivative of the top and the bottom, so the derivative of the top is 2x, the derivative of the bottom is 1 over x. Again, we try to simplify this expression so the x goes on top, so it becomes 2x squared. And then now as x goes to infinity, this goes to infinity. Okay, so we formed the fraction, computed the limit, and the limit goes to infinity. So we're in this case here. That means that the top function is faster than the bottom function. So that means that x squared ln of x is faster than ln of squared of x. So what this means is that say you have some computer data that takes up x bits. If you have an algorithm that say runs on the order of x squared ln of x operations, and a second algorithm that takes ln of x squared operations, then the first then in the long run, the first algorithm takes more operations, and so as a function, it grows faster than the second function. But as an algorithm, the second algorithm will be faster. So since it can become tedious to compare various functions by computing the limits all the time, there's sort of a general ranking that you can use to tell when one function grows faster than the other. So suppose P, Q, R, and S are positive numbers, then we can compare the following functions in the following ordering as follows. So generally, the natural logarithm grows very slowly. So any power of the natural logarithm grows slower. So this is the symbol for being slower than any power of x. Right, so this means that x to the p is faster than the natural log. And then now, a power of x is slower than if we take the same power of x and multiply it by some logarithm. And this in turn is slower than a power of x that is bigger than this power of x. And then in general, all of these are slower than exponential functions. So here a is a constant, so this is the exponential function, and this in turn is slower than x raised to x. Here x appears in both the base and the exponent. And so this is a sort of a general ordering of the relative growth rates. Right, so you can see that x squared ln of x is this kind of function here. So x is some power times some power of the natural log. And ln squared of x is this kind of function here. Right, so here q is 2. And so we see that this kind of function is faster than this kind of function. And so you can use this ranking to compare functions quickly instead of computing the limit. So the faster functions go in this direction.